Only the last part, that is van der Waals forces, is left, and then we will complete the chapter. And from next class onwards, we will start with a new chapter of physical chemistry. So this I have already told you what are van der Waals forces. So as you know that covalent bonds, they are held together by strong bonds, but the forces between these molecules are weak, and these weak forces are called as van der Waals forces. So the term van der Waal, it is used to describe all intermolecular forces. So whenever you are going to write van der Waals, always remember that V should be written as small, and D is also small, and W is capital. So there are several types of van der Waals forces. So this is the correct method of writing van der Waals name. It is the name of the scientist. V should be small, D should be small, and W should be capital. So first is your dipole, that is instantaneous dipole induced dipole forces. It is also known as, in short, ID forces. Basically, these are weak forces. They are also known as London dispersion forces. Second type we are going to read is permanent dipole. This London dispersion force is temporary, but next we are going to learn about the permanent dipole. That means PD forces. First force we are going to learn about ID forces, second PD forces, and the third force is hydrogen bonding. Just a minute. And the third force we are going to learn about is hydrogen bonding. Hydrogen bonding, it is a stronger form of permanent dipole force. Basically, it comes under PD force. So the stronger PD force is called your hydrogen bonding. And in detail, we'll learn about these forces in the next slide. So write down these three types of van der Waals forces which we are going to learn today: ID forces, PD forces, and hydrogen bonding. Okay, so first we are going to learn about hydrogen bonding. So it is the strongest form of intermolecular bonding. It is a type of PD forces because it is permanent. So how hydrogen bonding can occur? So there are some conditions. For hydrogen bonding to occur between two molecules, we need two things. First thing is we need a molecule to have a hydrogen atom, of course, because hydrogen bonding we have to do. It is covalently bonded to F, O, or N. These three are the most electronegative element in the periodic table: fluorine, oxygen, or nitrogen. And the second molecule to have a FON atom with the available lone pair of electrons. For example, this HF. Okay, so this is a molecule which is having a hydrogen atom. It is covalently bonded to fluorine. And the second molecule we need to have an FO or N atom with an available lone pair of electrons. Okay, so we can take any molecule, CH3F we can take, or we can take HF also. So HF and HF, it forms your hydrogen bonding in between HF molecules. Okay, so in hydrogen bonding, we need two things. Hydrogen atom should be there and an electronegative atom. Always there should be fluorine, oxygen, or nitrogen. If there is chlorine, then no hydrogen bonding will occur in this case. See, there is an example of hydrogen bonding. NH3. Okay, for example, this is your NH3. It is a hydrogen atom. It is covalently bonded to very electronegative atom, that is nitrogen. So bond is polarized, right? Because hydrogen is having partial positive charge. Nitrogen being electronegative, it is having partial negative charge. Okay. So when we have a neighboring NH3 molecule, this nitrogen, which is having a lone pair of electron, this is a necessary condition. It can form bond with this hydrogen atom. So this is the hydrogen bonding between two ammonia molecules, and we represent the hydrogen bonding by dots. Okay, so two conditions are satisfied in this example. So write down. Okay, now last topic is your peculiar properties of water. Okay, so first property is enthalpy change of vaporization and boiling point. Water has a much higher enthalpy change of vaporization and boiling point than expected. Why it happens? Because of extensive hydrogen bonding in water. So you can draw the extensive hydrogen bonding in water, right? H2O. This is the electronegative. A hydrogen atom is attached covalently with this oxygen atom. And this is H. This is your H2O. So this is your hydrogen bonding between hydrogen and oxygen. So water has much higher enthalpy change of vaporization and boiling point than expected. What is the boiling point of water?
100 degrees.
Yes, so it is higher. Why? Because of extensive hydrogen bonding. And what do you mean by enthalpy change of vaporization? Enthalpy change of vaporization. It is used in the thermodynamics chapter, which we are going to cover next, that is chemical energetics. So it is the amount of energy that must be added to the liquid substance, okay, to transform it into vapors, is called enthalpy change of vaporization. Writing amount of energy that must be added to liquid to transform it into gas, vapor. So write down first property of. So see, this is the graph. Enthalpy change of vaporization is on y-axis and number of electrons is on the x-axis. So you can see that H2O, it has a higher enthalpy change of vaporization as compared to H2S, H2Se and H2Te. Why? The reason you can write is extensive hydrogen bonding. Now the rise in, okay, so you have to draw this graph in your notebook.
Hey students! Interested in boosting your studies? Enroll now at Keddy Edtech. We offer online tuition for the Cambridge curriculum, grades 6 to IGCSE, AS, and A-level. Start learning with us today.
Okay, so you can see here that H2O has the highest enthalpy change of vaporization, but here in the graph there is a slight rise in the enthalpy change of vaporization from hydrogen sulfide to H2Te. Why? Because of the increasing number of electrons in the group 16 atom as we go down the group. So atomic number increases, number of electron increases. So this leads to increased ID-ID forces. So ID-ID forces, instantaneous dipole, induced dipole forces increases when number of electron increases because the molecule will get bigger. So more it can induce. If water only had instantaneous dipole induced dipole forces, okay, not hydrogen bonding. If only water have what ID forces, not hydrogen bonding, so its enthalpy change would be around 17 kilojoule per mole. But here you can see that water enthalpy change of vaporization is approximately 42 kilojoules per mole because of extensive hydrogen bonding. So why enthalpy change of vaporization of water is higher? Because water is extensively hydrogen bonded. So this is the explanation of the graph. Write it down. So under the topic peculiar properties of water, first property we have studied enthalpy change of vaporization. Okay, enthalpy change of vaporization and hydrogen bonding, right? Enthalpy, sorry, boiling point. Enthalpy change of vaporization and boiling point. Second property is surface tension and viscosity. The water has high surface tension, high viscosity. Okay, hydrogen bonding reduces the ability of water molecules to slide over each other. So viscosity of water, it should be high or low. Viscosity means resistance to flow. So water easily flows, right? So water easily flows. The viscosity of water should be low. The hydrogen bonds in water also exert a significant downward force at the surface of the liquid. For example, this is my liquid. Okay. So this is my water. So we have hydrogen bonds here. So this hydrogen bonds, they exert a significant downward force on the surface of the liquid. This causes the surface tension of water to be higher than most liquids. So water has a higher surface tension and viscosity should be low for water. Viscosity means resistance to flow. For example, honey. So honey, the viscosity of honey is higher because honey resists to flow. So the reason is same. Water has a particularly high surface tension due to strong hydrogen bonding between its molecules.
On this, you've written hydrogen bonding reduces the ability of water molecules to slide over each other. So the viscosity of water is low. I feel like it's contradicting each other.
Which statements are contradicting each other?
Hydrogen bonding reduces the ability of water molecules to slide over each other, so the viscosity of water is low.
Hydrogen bonding, it reduces the ability of water molecules to slide over each other. The viscosity of, yes, they are contradicting each other. So don't write this line. Write down only viscosity of water is low. Viscosity of water is low.
Okay.
Okay, I'm writing the correct explanation here. Water has a low viscosity due to its molecular structure. and strength of intermolecular forces. So as we know that water molecules, they are held together by the strong hydrogen bonds, but these bonds, they are not as strong as in more viscous liquids. So we can say that the close packing of the water molecules and the relatively low molecular weight of water, it contributes its low resistance to flow. So although they have strong hydrogen bonds, but not as strong as those in the higher viscous liquids like oil and syrup. I think it's clear now that all the water molecules are relatively small. They are having a bent shape. So we can say that water molecules are packed together to have a close structure. But they are not as tightly packed as the intermolecular interactions in the more complex molecules in the more viscous liquids like oil and syrups. So in comparatively, water has a low viscosity. In this figure, what you can see?
Ice, water, clouds.
That means ice floats on water. So why ice floats on water? Since it is a solid, solids have higher density. So ice is less dense than water. Most solids are denser than their liquids because of their higher density, higher molecular weight. They are packed closely in the solid state. But this is not true in case of water. Why? Due to its structure. So in ice, there is a three-dimensional hydrogen bonded network of water molecules which produces a rigid lattice in which each oxygen atom is surrounded by a tetrahedron of hydrogen atoms. So this gives us more open arrangement due to the relatively long bond lengths of the hydrogen bonds, and it allows the water molecules to be slightly further apart than in the liquid. So there are more vacant spaces. So if there are more vacant spaces in this, so density of ice is less than as that of the liquid water, and that's why we call that ice floats on water. Okay, so the simple question, why ice floats on water, the answer lies in the structure of ice. Write it down. So this ID forces I already explained. Here examples are written like neon, argon. These are my noble gases. They exist as isolated atoms. Okay, they can be liquefied but at very low temperature. So there must be very weak force of attraction between their atom, and that weak forces is ID forces. These weak forces, they keep the atoms together in the liquid state. Bromine, it is a non-polar molecule which is liquid at room temperature. Weak forces of attraction, that is ID forces, they are keeping the bromine molecules together at room temperature. So these are some examples of ID forces which are also known as London dispersion forces. So write down the examples. We take a screenshot of this slide, PD forces. This is the example of permanent dipole forces. So the forces between two molecules having PD forces is acetone. This is acetone and acetone. So the attractive force between the partial positive charge on one molecule and a negative molecule. Okay, so this gives you weak attractive force between the molecules. Here the charges are developed, which are permanent. Oxygen is partially negative and carbon is partially positive. So they have permanent dipoles developed here. So that's why it is PD force.